Welcome back. As our next speaker, I had the pleasure of having Cindy Rush from Columbia University. She'll be talking about high-dimensional statistics. I cannot read her title right now, so I'm sorry about that.
Oh,
Yeah.
that's the problem. How did it go all the way over there? Wow.
I don't
Okay.
know. I think you
Yeah.
just kept pressing the button to
Yeah,
test
I
the
guess so.
pointer, and
Here we
that's
go,
what
here we
happened.
go.
Yeah. Okay. So that's the title.
Okay. Thanks, Roberto. All right. Thanks to the organizers. It's really nice to be back in Rio. I spent Sunday at the beach, which was quite nice. All right. So I'm going to talk today about approximate message passing algorithms, in particular related to a specific problem, which is that of studying this sorted L1 penalized estimator and how we can use approximate message passing algorithms to give kind of precise high dimensional asymptotic characteristics of the estimator itself. So this is based on a series of works over the last, kind of like 5-ish years with many folks. So they're listed on the screen. Okay, so basically the problem we're going to think about is the following. We're going to study a sorted L1 penalized estimator, which I'll call slope, and this is basically a generalization of the lasso. So I'll introduce what these estimators are if this is a bit unfamiliar. And this estimator was proposed as a way to improve on the lasso, and in particular as it relates to model selection, right? So specifically to reduce the kind of false discovery. So one of the types of errors you can make in these sorts of problems. So what we'll talk about is approximate message passing algorithms, or AMP, as a way to give exact statistical characterizations of both these estimators and the large system limit, and then we'll use AMP to compare the performance of the two. So basically, what I'm going to do is, start the talk by introducing slope, so we have an idea of the problem we want to study. But then I'm going to just discuss AMP generally as a framework for studying kind of high-dimensional asymptotics for a large class of estimators. So namely those that can be constructed as minimizers of, a sort of random cost function. And then we'll, kind of show like what this buys us in terms of slope specifically, and discuss a little bit about how AMP plays a role in the proof. So there's kind of I think AMP has like many uses, and one was mentioned yesterday by Keith, right? It can be used to study these statistical computational gaps in problems. So it's amongst the classes of algorithms that we believe to be optimal for many problems. So AMP is kind of one class of algorithms that for many problems we believe that if it can't solve the problem, then no polynomial time algorithm can solve the problem. So there's one angle of AMP that's that, which we won't discuss so much. The kind of the angle of AMP that we will discuss is kind of its role as sort of a proof method for studying high-dimensional properties of statistical estimators amongst other sorts of estimators. Okay, so this notion of kind of sorted L1 penalization can be used in many types of statistics problems. We're going to think about kind of the simplest sort of stats problem, or at least the simplest sort of like high-dimensional statistics problem, which is that of high-dimensional linear regression. So the basic model I'm thinking about is the following. So I have data X and Y, right? So X is kind of like my feature matrix, right? My design matrix if you're an engineer, perhaps. And then Y is the output, and they're related in the following way, right? So we have linear measurements of some unknown vector beta, right, that come from our matrix X, and then we have some noise that's given by Z. And in particular, this problem is high dimensional, right, in the sense that when we look at the dimensions of this matrix X, which is, in rows and P columns, right? We're thinking about P being as large or perhaps larger than N, the number of rows, right? In general, right, if we just have X and Y, there's an infinite number of betas that can relate them exactly. So we have to assume some sort of additional structure in this high-dimensional regime. And in particular, a common assumption of structure for high-dimensional statistics, right, is that of sparsity. So what this means, right, is I'm going to assume throughout the talk that, I have a signal here that I'd like to recover, right? This is the kind of target of inference. This is the thing I'd like to find, right? I'm going to assume a prior distribution on the elements of that signal. And a particular feature of that prior distribution is that there's a linear sparsity, right? So in particular, there's only the probability of any element being non-zero is epsilon, right? So that vector is going to have a bunch of zeros and approximately p times epsilon non-zeros, right? So in particular, to think about model selection, right, what we're kind of thinking about is, if this is a matrix of features, then the question is kind of which of those features is actually related to the output, right? And so the relevant features are those that correspond to kind of the non-zeros and the signal beta. All right, so the goal, we have X and Y, and I'd like to recover beta. How do I do this? Well, kind of the way that statisticians do this, right, is to, instead of searching over all possible betas, they constrain the search space through some sort of regularization. And in particular, the most common sort of regularization is that using the L1 norm, right? So if you find an estimator that's regularized with the L1 norm, then this gives rise to the lasso, right? And so what is the lasso, right? Well, okay, it's an estimate of this vector beta, right, that's constructed by minimizing a cost function using, our output y and that data matrix X, right? And what is the cost function, right? Well, we have a data fit term, right? This is just the sum of the squared errors. And then we have our regularization term, which is the L1 norm, right? And the amount of regularization is controlled by this parameter lambda, right? So if lambda's large, right, we really kind of regularize the solution. The output's going to be very sparse. If lambda's small, then the output will be more dense, right? So lasso is widely used, right? This is basically the way that people solve high-dimensional linear regression. It's like a few years ago when the girl was able to produce the pictures of the black hole, right? That was basically like lasso in action, as it turns out. So this is how people kind of solve these problems in the real world. So there's something there's some limits to lasso. So for example, if we want to find the optimal amount of regularization, right, the optimal kind of lambda in order to perhaps minimize your mean square error or something, you need to know things that you wouldn't know in practice, like the actual sparsity in the signal and these sorts of things. And so one of the motivations for slope was to kind of get around this aspect of things. So slope is a generalization of the lasso that looks like the following. So you still create an estimator that's a minimum of a cost function, where the first term is your data fit term and the second term is the regularization. But now your regularization is slightly different. So it still uses a kind of L1 regularizer, but the idea is you sort of sort the entries, and the larger entries get paired with kind of a larger amount of regularization. So now we've moved from kind of one lambda value with the lasso to control the amount of regularization to a vector of values, and we pair the kind of the large regularizers with the large elements. So why would we do this? Well, there are a few kind of motivations. One I mentioned is, you know, the lasso, in order to optimize that lambda, you need to rely on things you don't know. Here, this is more adaptive, right? It in some sense adapts to the data in a way to give the regularization. The other idea is to control the false discoveries. So to control, you know, the elements in our estimate that are non-zero when the true value is 0. And so why would you want to control this, right? Well, you can think about, like, in practice, if you're trying to relate, like, I don't know, gene expressions to the presence of some disease, right? If you're the statistician and you say, like, okay, X, Y, Z genes are related to the disease, but in fact, you know, X and Y are not, then what you've done is, you know, the biology community is going to spend a lot of money investigating this sort of relationship that doesn't actually exist. So, you know, this is something that you want to control if you're a statistician. And so why would we think this should do that? Well, it kind of goes back to one of, like, the classic results in statistics, which is related to multiple hypothesis testing. So the idea is kind of the following, right? If you do a hypothesis test, you know, you want to test between two kind of realities, let's say, and you set some sort of significance level. And the idea is if you do 100 of these tests, then the sort of the significance level you've set is meaningless, because it's you know, something that says, well, even if there's no sort of change that needs to be made, 5% of the time, you know, I'll kind of say that that's true. And so if you do 100 of these that are, you know, kind of either all related or all independent, then now you've kind of killed this notion of significance. So, like, one of the kind of classic results, like the most highly cited papers in statistics, is due to Benjamini and Hochberg, that does a correction for this kind of multiple hypothesis testing. And so the idea there is if you do many hypothesis tests, you should pair the kind of most significant results with the most stringent p-values, right? And this is kind of mirrored by what we're doing here. Like, at some level, when you're searching for, you know, a sparse vector in high-dimensional linear regression, you're doing a multiple hypothesis test. You're looking at each element of the vector beta, and you're saying, is it 0 or not? And so especially in this high-dimensional regime where I'm thinking about, you know, p being larger than or the same size as n, and both of them perhaps growing to infinity, then we need to correct for the fact that we're doing many hypothesis tests. So in the same way as Benjamini-Hochberg, what this does is kind of pairs the most significant coefficients with the most regularization. So there are some nice properties of slope. So I'll just mention, right, lasso is obviously a specific case of slope. If I just made all of these, you know, all of these inequalities equalities, then we've got lasso, right? But even though lasso is a specific, you know, instance of slope, there are some nice properties that slope has that maybe lasso doesn't. So, you know, in particular, it achieves minimax estimation properties without requiring knowledge of things that we perhaps wouldn't have in practice. Like the degree of the sparsity in beta, and it also provably can control the false discoveries and, you know, at least some kind of toy problems, let's say. And, you know, the nice thing is this regularizer is still a norm. The cost function remains convex, and so you can, you know, efficiently solve it using, like, proximal gradient descent. Okay, so. So what you know, what the rest of the talk, well, what I'm aiming to do is I want to kind of compare the properties of slope with the properties of lasso, right? So we've generalized the lasso. I've gone from, like, one tuning parameter to p tuning parameters. So you would hope that you can get some benefit from that. And so, one of the questions we ask are, can we provably say something about the benefits of slope? So this is what we wanted to study. And the tool that we decided to use was approximate message passing. So what I'm going to do now is just kind of pivot a little bit and talk about how AMP can be used as sort of a proof method for studying properties of estimators like the slope and lasso. So I'll just start with a little bit of an introduction to approximate message passing, or AMP. So this is a class of iterative algorithms, efficient iterative algorithms that have been applied to many kind of statistical estimation problems. So linear regression compressed sensing, like we're talking about here, also in generalized linear models, and then in various forms of low-rank matrix estimation. So including like the stochastic block model that Keith talked about yesterday. It also has a few practical applications. So there's some kind of limitations in the sense that we have to assume some real structure to that matrix X. And so in particular, what we'll assume is that the entries are IID Gaussian. So when you think about actually applying AMP, it's most useful in settings where an assumption like IID Gaussian entries to that matrix X is appropriate, right? So in particular, that's not the case if you're like a statistician and that's a data matrix. Like IID Gaussian doesn't model data well, but if you're an engineer and you want to do communications, wireless communications, or compressed sensing or imaging, right? If you're an engineer where you can kind of design the system, AMP can be used actually as a practical solver as well. So the original kind of derivation of AMP was based on approximating loopy belief propagation algorithms for the problem of compressed sensing. So sort of the idea is you construct a factor graph that relates the coefficient vector beta that you'd like to find to your output y, right? If that A matrix is, has no zero values, then this factor graph will be completely dense. And so on that dense factor graph, you can, set up a belief propagation algorithm, right? Like a min-sum message passing algorithm. Of course, there's no guarantees that this is going to converge or do anything nice because we have a dense factor graph. But nonetheless, you can kind of imagine running that algorithm. And basically, the way that you move from that to AMP is through kind of two approximations. So the first is that, since the factor graph is dense, essentially all the factor to variable and variable to factor messages are approximately the same value, right? They all only differ in the edge that's kind of left out when they combine the previous messages. And so the first thing you do is kind of approximate all of the nodes in one direction with a single value. And this results in kind of a simple two-step iteration. And then the second approximation you make is instead of passing the full kind of data beliefs, you just approximate the full kind of densities, right, by just the first two moments. And out pops kind of the AMP algorithms. So this is how they were sort of originally derived. I won't go much into this, but I thought I'd just give you a flavor of where this comes from. All right, so there are kind of two attractive features of AMP, right? So the first is that it's easily tailored to prior information on the structure of the signal itself, right? So kind of the idea that I always have in mind is like, for low-rank matrix estimation, if you perhaps know that the spike that generates the matrix is sparse or something, it's hard to incorporate that information into spectral methods, right? However, AMP can easily kind of handle these sorts of assumptions naturally. And the point that we'll focus on is that for some measurement matrices or for some kind of assumptions on that matrix X, the AMP theory gives us precise asymptotic characterizations of the performance of the algorithm in this sort of large system limit. So kind of the asymptotics I'm thinking about this entire talk are those where both kind of dimensions of the problem are growing in a proportional sort of way. So as I mentioned before, right, AMP also kind of plays a fundamental role in understanding the performance gap between information theoretically optimal and computationally feasible estimators, right? So this is that statistical computational gap, right? In a sense, AMP is complementary to like the overlap gap property that David told us about on the first day, right? These are both kind of ways to say something about the computational limits of problems. Okay, so what we'll talk about again is, right, the fact that we can use the AMP theory to give us precise asymptotic guarantees for many statistical procedures, and we're going to use AMP to study like lasso and slope. Okay, so what I'm going to talk about is kind of a program that we laid out in this tutorial I wrote a few years ago with my colleagues. That's a way for systematically deriving exact expressions for the asymptotic risk or kind of other properties of estimators that are solutions to like a class of random optimization problems. So in particular, this is the model that I'm thinking about, right? So I'm thinking I have some output y. So I introduced like high dimensional linear regression. And this is what we're going to go back to study when we talk about slope and lasso. But what I'm doing now is showing kind of a more general regime where AMP can be used. So in particular, now instead of thinking about like linear regression, I'm kind of thinking about generalized linear models, right? So the idea is if I have some output y that's still based on kind of linear measurements of my target of inference beta, but now I can like allow these linear measurements to be wrapped in some link function, so long as I assume that that function's known, right? Basically, we can use AMP to sort of solve for beta in some sense. So throughout, right, I'm going to assume that my matrix X is IID Gaussian, right, and my vector beta is the thing I'd like to recover. So, okay, if you have like data that you believe are generated by these kind of generalized linear models, then a common way to recover the vector beta is through the minimization of some cost function like the following, right? So in particular, like lasso is an example, and slope nearly is an example. So I'm going to think about optimization programs of the following. So I have an estimator that minimizes a cost function, where the cost function, again, is some data fit term represented by some general loss function here, and then some regularization or penalty term. And I'll assume that they're both convex in their first argument. And so there's a number of estimators that have these properties, right? So the maximum likelihood estimator, the maximum a posteriori estimator, things like lasso, slope, ridge, whatever your favorite kind of regularization is, right? So basically, the way that we can use AMP and to study these estimators is the following. So it's sort of easy to write down an AMP algorithm whose fixed point solves the optimization, right? So in particular, like I know how to write down an AMP algorithm that if you initialize it randomly, let's say, then the fixed point of the algorithm is going to be one of the minimizers of this cost. Right? Sorry, okay. So if you want to use this approach, you need to characterize the fixed point. Okay. Associated with the AMP algorithm, there's a state evolution that describes the dynamics of the algorithm. So it describes the performance of the algorithm. There you would also need to study kind of the fixed point properties. And then you need to show that the AMP converges to its fixed point. So this is kind of the hard step, showing that the AMP will actually converge to its fixed point, especially if the cost function is not strongly convex. Okay. So basically, if you can do this, then what does that buy you? Well, loosely speaking, what this allows us to do is characterize the asymptotic joint distribution of the estimator with kind of the true beta that generated the data, right? And so then what you can do is under various forms of loss functions, you can characterize properties like the false discovery rate, the true positive proportion, the mean square error, the asymptotic sparsity, and so on, right? So basically what this does is it allows you to take kind of the theory for AMP that relates the state evolution to the dynamics of the algorithm and push that theory onto your minimizer itself, right? So sort of the idea is, I know statistically kind of the properties of the AMP algorithm at every iteration, and I know at its fixed point that I've solved this optimization problem, so then I can take the statistical properties of the algorithm at the fixed point and push them onto the estimator itself. Okay, so this is kind of the the program that we're using to study slope and lasso. And in particular, this has been, this program has been used many times in the statistics literature. So to study things like high dimensional properties of logistic regression. So this is what like Pragya Sur did in her dissertation. Also, slope, lasso, M estimators, and so on. Support vector machines, things of this nature. But we think that, there's probably a wider class of GLMs where this could be, this program could be used and hasn't been done so before. Sorry, I'm like losing my voice like Roberta was the other day. Okay. So now what I want to do is kind of use this program to say something about the model selection properties of the slope estimator. All right, so again, what we wanted to do is say, we've moved from lasso to slope. We've increased the number of regularization parameters, right? We now have P tuning parameters instead of one. Lasso is a specific case of slope, so we would hope that there's some sort of benefit to doing this. Right? And so our question was, can we kind of quantitatively characterize the benefit of this sort of sorted L1 regularization? So the way that we decided to study this problem is to study the model selection properties. So in particular, this is related to the number of false discoveries and the true positives found by the two estimators. So what I'm going to do is introduce the object that we're studying, which is this FDR TPP trade-off curve, show our main results, and then discuss a little bit about how AMP is used in the proof. Okay, so these are the assumptions that we're going to make. Again, my measurement matrix X is going to be IID Gaussian. I'm assuming a prior on my signal beta with a kind of fixed sparsity level epsilon. My noise I'm going to assume is IID with some finite variance. And my undersampling ratio, right, so the ratio of the size of my measurement matrix approaches some constant in the limit. The final sort of assumption I'm going to make is on these threshold values. So in particular, what I'm going to think about is these threshold values are the order statistics of IID realizations from some distribution lambda, right? And so the only property I assume of lambda is that it has sort of a finite second moment. And so I will mention that kind of all of these IID assumptions can be relaxed, but we didn't really pursue that here. Okay, and then what I want to study are these two values, the true positive proportion and the false discovery proportion. So the true positive proportion is going to be the ratio between the number of true discoveries, where by a true discovery, yeah, go ahead, I guess. Yeah. Yeah, so I'll discuss a little bit about what we think you should do in practice. What we're going to do is we're going to actually optimize over all possible lambdas when we compare lasso to slope. Or, in the sense that all possible lambdas are going to be, order statistics of IID draws from some distribution. I think in practice, how do people actually choose the lambdas? There's a few sort of suggestions. So one is to choose the lambdas as inverse Gaussian quantiles. This is related to the Benjamini-Hochberg procedure. So that's what gives you the provable control over the false discoveries in that setting. What I think I would advocate for is actually you get kind of most of the benefit of the generalization to slope by going to just the simplest slope estimator. So where instead of having one lambda for lasso, you have basically two values. So now you have three parameters, right? The large value, the small value, and the cutoff point. And so at least in the metrics we're kind of looking at, this sort of two-level slope seems to give you almost all the benefit of the full generality. There you can still think of this as IID draws from some, two-point distribution or something. We can kind of, using the AMP results, at least asymptotically, we can find optimal lambda sequences in many problems, especially if you limit yourself to the two-level. The issue is they aren't really analytic. You have to do some sort of, numerical thing. So it's hard to write papers about that at some level. Okay, so what we want to look at is true positives and false discoveries. So again, true positives are going to be the following. This is the number of elements of our estimator that are non-zero that correspond to non-zero values in the truth, right? So these are true positives in the sense that, we think that kind of feature is actually related to the output truly, and we've discovered it, right? False discoveries, right, are those elements, the number of elements of our estimator that are non-zero, but they correspond to, true zero values, right? And so what we'd like, of course, is the true positives, the TPP to be high and the FDP to be low, but you can't optimize these simultaneously, right? If the TPP increases, the FDP increases, and so on. There's some sort of philosophical discussion that could be had about, what do you actually mean by true discovery and real data sets, but I've kind of assumed my way out of that discussion by, having an IID Gaussian measurement matrix there. But that's, also a fun conversation to have if, over drinks or something. Okay, so our aim is to characterize the optimal trade-off between the false discovery and the TPP for slope. So what do I mean by this? We want to kind of characterize the following trade-off curve, as I'll call it. So for every possible value of TPP, right? So if I look at, true positive proportion between 0 and 1, for any fixed value of that, I want to find the smallest possible value of the FDP that slope can provide if I optimize over any sort of regularization sequence. So I find the best lambda sequence. And also I'm going to optimize over any epsilon sparse prior. So in fact, I could give myself kind of incredibly large signal to noise ratio in the problem, right? So what this kind of boils down to is I have now two parameters that describe the problem. One is delta, that undersampling ratio n over p. The other is epsilon, my sparsity. And what I find is for any value of the TPP, the smallest FDP that slope can give us. So I'm going to, one of the reasons we decided to study this particular object is that in the case of the lasso, this sort of fundamental trade-off has been rigorously characterized first by, Dave Donahoe and Tanner, and then, more recently it was studied again by my colleague Weiji and his collaborators, Bogdan and Candace, right? So in the case of the lasso, this is what's known, right? So here we're looking at two images of this trade-off curve for different delta epsilon pairs, right? And so the TPPs on the x-axis here, the FDPs on the y-axis. Obviously, what I'd like, right, is false discovery small, TPP large, right? So it's kind of like this bottom right corner is the region I'd like to be in, right? But what we see for the lasso, right, is that in both of these settings, right, for both of these different kind of problem settings, that bottom right corner is unachievable, right? So what this says is that, for the lasso at least, it's impossible to have high power and low false positive simultaneously, irrespective of like the amount of regularization you use, and also irrespective of kind of the signal to noise ratio in the problem itself. And in fact, for the lasso, for certain problem parameters, so for certain kind of delta epsilon pairs, the true positives can be strictly bounded away from 1, right? So this is the example in this plot, right? So what this says is no matter how many false discoveries you're willing to tolerate, the lasso in this setting is never going to be able to find all your true non-zeros, right? And so what I'm going to call is this kind of largest achievable TPP in the lasso as the Donahoe-Tanner power limit. And so it should come as no surprise that this sort of power limit occurs in problems that are hard, right? So, this is kind of a delta epsilon plane that characterizes when this power limit happens for the lasso. And basically this says, when epsilon is large, so your signal is dense, or when delta is small, meaning you're like got a really short fat matrix there, you're going to see the phase transition, right? So when the problem's hard, the phase transition occurs. Yeah, David?
So these are the trade-offs for the lasso, which is a specific algorithm. Are they consistent with information theoretic trade-offs, or they are not known? What do we know about information theoretic? In other words, computationally unlimited.
Yeah, I don't know if we know the information theoretic kind of limits here. Yeah, I mean, we know the information theoretic limits, often we study the MSE, right? And not like these sorts of, it's a good question. I don't think it's known. Okay, so what we said is like, okay, so what we want to do is kind of look and see how slope performs like on these same sort of kind of model selection properties. So the first thing we did, right, was like simulate. And so here what we've done is just kind of run a number of independent problem realizations for both slope and lasso, where we've changed kind of the lambdas for both across a range of values, and then we've plotted the realized false discoveries and true positives. So here, lasso's and the red points, slope is the blue points. And we plotted just kind of two different delta epsilon realizations in both of these plots. And so what we're seeing, right, the lasso realizations are kind of consistent with this true positive upper bound that we saw on the previous slide, right? So in both cases, the red points, are not, there's no true positives above like 0.5 here, maybe like 0.4 here, right? And so these are problems where there is a Donahoe-Tanner power limit, and we're seeing it, of course, in the simulations as well. On the other hand, right, slope doesn't seem to have that same sort of power limit, right? For these problems, the slope estimators seem to be able to find all the true positives so long as we sacrifice some of the false discoveries. So this kind of led us to ask, right, why is the sorted L1 regularization better in this high TPP regime, right? So what is allowing slope to beat this Donahoe-Tanner power limit that exists for the lasso? And then, is there anything interesting that slope gives us in this low TPP regime and the part before the Donahoe-Tanner phase transition? And so our main results are the following. So basically what we aimed to do, again, was just to kind of characterize this trade-off curve for slope that exists for the lasso. It turns out that we weren't able to get the curve exactly. We were only able to get upper bounds and lower bounds. The reason being that it's just basically the problems like, we've got, P kind of things we're optimizing over now in that vector of lambda values, and P is going to infinity. So in some sense, we're doing like an infinite dimensional optimization in order to produce these curves. So this is one of the reasons, we also have kind of a non-separable penalty, right? If you think about like that sorted L1 function, like every output depends on every input through the sorting step. So just the analysis is a bit more complicated. But what we were able to find is tight upper bounds and lower bounds on this curve, which I'll kind of show you in pictures. So in particular, what we're looking at here is just a specific delta epsilon pair for slope. And the results, or the upper bound that's given in green and blue, and the lower bound that's given in the kind of red dashed line. And then this plot just kind of zooms in on the left-hand side. And the colors kind of correspond to how we actually prove the upper bound, basically. So first, if we look at the upper bound, right, what are we asking? Well, so for slope, right, lasso is a specific instance. So in particular, the lasso curve can serve as an upper bound for slope, right? We know that if lasso can achieve this TPP FDP pair, then slope can at least do it as well, and perhaps better, right? So the green part of the curve is just the lasso curve, right? Which serves as kind of a trivial upper bound for slope, but it stops at some point because of that Donahoe-Tanner phase transition, that TPP upper bound. The second part of the upper bound, we actually use A and P to find, right? So the idea was this upper bound is constructive in the sense that we select kind of a lambda regularization sequence and a prior distribution that allows us to find these FDP TPP pairs. And the way that we do this is by kind of that program I gave you earlier that allows like AMP to tell us properties of estimators in these asymptotic limits. Right, so I won't say much about the lower bound, right? This is the red curve here, but basically we just kind of knocked our heads together until we could simplify the like infinite dimensional optimization problem in a sense that we could at least numerically get kind of lower bounds. And this is what is given in the red curve. So These are just some plots for different kind of delta epsilon pairs to try to convince you that even though we don't know the curve for slope exactly, we have a pretty good understanding of where it is. The upper bounds and lower bounds are fairly tight, right? So in particular, you know, these guys, we fix an epsilon, we fix the sparsity level, and we change the undersampling ratio of the problem. And the bottom curves, we fix the undersampling ratio, and we change the sparsity. And in all of the cases, the lower bound and the upper bound are pretty close together. I'll skip this slide so we can wrap up. I'll also mention that we have another result that's perhaps like more of a natural question for folks, which is sort of an instance superiority. So it basically says, you know, now I'm thinking about a situation where, you know, you give me a prior distribution on the signal. So you believe you're solving a problem with this sort of prior on the signal. You give me a lasso lambda that you'd like to use. And what we can prove is that, in fact, there always exists a slope lambda sequence that improves on the lasso in all of the following senses. So in particular, you know, the true positives of slope will be larger, the false discoveries of slope will be smaller, and you don't have to sacrifice in terms of prediction in order to get the better model selection, right? So, you know, before when we were looking at the curves, we were kind of optimizing over the prior distributions, and this says that if you fix the prior distribution, then, you know, there's always kind of a slope sequence that will outperform. Okay, so to wrap up, I just wanted to talk a little bit about the proof of the upper bounds here. So in particular, the proof of this piece, right, that uses AMP. So the idea is sort of the following. So mathematically, why is it that slope can kind of beat this Donohoe-Tanner phase transition? Well, one of the reasons is the following. So what we know about the lasso is that in this sort of proportional asymptotic regime, the lasso is going to select at most n of the n non-zeros in its estimator, right? So beta hat is a p-length vector. The number of non-zeros that the lasso outputs is upper bounded by n. And moreover, you know, what we know, this is, you know, kind of what Weigia found in his dissertation, is that a significant proportion of these non-zeros in the lasso solution are going to be false discoveries. So in particular, as you kind of change the lambda value for lasso to allow more non-zeros in your solution, you're going to pick up kind of incorrect estimates along the way, and this is somehow unavoidable. If we think about slope instead, the kind of the corresponding upper bound here is the following. So there's still an upper bound on the non-zeros in the slope solution, but the upper bound is on the number of unique non-zero values in the slope solution. So one of the kind of characteristics of the slope estimator is that, you know, many of the non-zeros in your estimator take exactly the same value. And this is kind of, you can kind of see this if you look at like the proximal operator associated with this like sorted L1 penalization. And so the bound is not on the number of non-zeros, but the number of unique non-zeros. And so in some sort of extreme case, the signal can still be completely dense, right? In which case, like trivially, you have TPP equals 1. It turns out that, you know, in this kind of, this is not always what's happening when you beat the TPP upper bound, but, you know, this is kind of, I think, one way to kind of understand how slope gets around this. Okay, and so just, how do we prove this upper bound? Well, so kind of the idea is that we use AMP to exactly kind of characterize the asymptotic faults discovery and TPP for a specific slope instance. So in particular, we look at the kind of simple two-level regularization, that I was mentioning before in response to Mickey's question, right, where instead of having, p different values in the slope regularizer, you just choose 2 and like kind of a proportion. And then, using this, you can kind of characterize the slope trade-off curve exactly to show that it overcomes the Donahoe-Tanner power limit. So in particular, right, what does this give us? Well, AMP tells us an asymptotic characterization of the slope estimator in terms of the AMP state evolution, right? So the like scalar recursion state evolution, which describes the dynamics of the AMP algorithm, will now tell us something about the asymptotic TPP and FDP for slope. This allows us to study properties of the estimator, like the sparsity, the FDP, the TPP, also the mean square error, and things like this. And it basically leads to constraints on delta epsilon pairs for achievable FDP, TPP that then can be kind of translated into this trade-off curve. Okay, so that's where I'm going to wrap up, and I'm happy to take questions if there are any. Maybe I'll just say something about open questions, right? Obviously, we'd like to characterize the trade-off curve exactly. It turns out in the case of two-level slope, we can, right? But we'd like to do it for p-level slope. Of course, we'd like to extend beyond, the assumption of the IID Gaussian matrix X. And there's sort of recent work in the AMP literature that extends the AMP theory to quite general classes of measurement matrices. So this has been led by Chen and Lam, Zhou Fan from Yale, Rishabh Dudeja, who works with Keith and Josh, Subrata Sen, and Yue Liu, both at Harvard, right? And this is all, now this kind of extends the AMP theory to really wide classes of measurement matrices. So for 10 years, we basically only had the AMP theory for IID Gaussian assumptions, and then these guys, came along and, Fan makes assumptions only on kind of the spectrum of the matrix, which gets us pretty close to kind of real-world data problems. The work of Yue, Subrata, and Rishabh handles semi-random matrices as well as things, I think Fourier matrices and these sorts. So at least for the kind of the direct AMP theory, we have extended to well beyond the IID Gaussian measurement matrices at this point. We'd also like to be able to say something actually to practitioners about optimal or useful regularization sequences. We can, we're getting kind of close, at least in the case of two-level priors, but it's a little bit of a shame that you can't say something analytically, or we're unable to say something analytically at this point, but hopefully at some point at the future. So I'll stop there and take some questions. Thanks. Yeah. Yeah, it's clear that, we can kind of construct specific instances where we beat the two-level curve. So the two-level is not optimal, but if you look at these pictures, the upper bound is the two-level curve, right? So, you're only getting a little bit more when you go into the full generality. The thing I skipped is kind of interesting too. Obviously with slope, you're getting, you're beating the Donahoe-Tanner phase transition, but even below the phase transition, you get a little bit with slope. So like, I kind of skipped this because it's hard to describe, but the gray area is the upper bound and the lower bound for slope. And it's like, it improves on lasso even below the Donahoe-Tanner phase transition, but just a little bit, So, yeah, I mean, I think, my feeling is that the curve is closer to the upper bound than the lower bound. And I mean, as I mentioned, my feeling is that like the 2-level slope is probably, in terms of like, trade-off between like how much of a headache tuning parameters are versus like what you gain, that's probably at least the balance right now that I would suggest. So. Yeah.
So have you thought about like a family of like, so we have P parameters, have you thought about like reducing to fewer branches and like a family of lambdas that like can try to get close to this balance? Like if the family contains all ones, then we have last, so maybe another family like with 2 parameters.
Yeah. So like, I guess like the like simplification that we've considered a lot, right, is instead of fitting P different values, like you choose like a lambda big, a lambda small, and then you try to optimize for kind of what proportion gets the big value, what proportion gets the small value. So like this is easy because instead of having 3 parameters, instead of having P parameters, you now have 3 parameters, right? And that like, at some level you can even cross-validate on 3 parameters for most problems. So that's the simplification we've considered the most. There are, in fact, there are other kind of, I think, simplified classes you could think about, but this is the one we've studied the most. And like kind of as you suggest, like that simplification gets you like a lot of the benefit. So. Yeah.